So now we'll discuss the application of the first law of thermodynamics. Okay. So the first law of thermodynamics can be used to find the heat capacities of some gaseous system. Heat capacities are this P and Cv. You know, Cp is the specific heat capacity at constant pressure and Cv is the specific heat capacity at constant volume. Now, according to the first law of thermodynamics, we know that dq equals to du plus dw, or dq equals to du plus p dv. Okay. Now, this U, as you know, is the internal energy. We have said that the internal energy is a function of temperature, that we know. But in general, the internal energy can also be a function of the volume of the system V. Okay. So, we can say that the internal energy U is a function of both these independent variables, temperature T and volume V. They are independent means these two variables, state variables, do not depend on, their values do not depend on each other. Okay. So, U can be written as U as a function of temperature and volume. So, we can write du equals to del U del T constant V dt plus del U del V at constant T dV. Okay. Now suppose this is equation 1 and this is equation 2. Okay. Now we will put this value of du in equation 1. Okay. So putting value of du in equation 1. So what do we get? We'll have dq. Okay. Then we'll have the value of du. Okay. So we'll have del U del T constant V dt plus del U del V constant T dV plus this P dV. Okay, so P dV. Next, what we can do? We will keep this term as it is. Then from these two terms, we can take dV common. Okay, so we'll take dV common from these two terms. Okay, so we'll have del U del V constant T plus P into dV. Okay, or just we'll do some rearranging. Okay, in this step. So we have the first term, then we will write, suppose P as first. Okay, so P plus del U del V constant T dV. Okay, so now if we divide this whole equation by dt, okay, then what we'll have? On the left hand side we will have, dividing this whole equation by dt, on the left hand side we will have dq by dt equals to del U del T constant V, so dt by dt will be equals to 1 plus P plus del U del V constant T then dV dt. Okay, so suppose this is equation 3. Okay, now if this volume V is constant, then this whole second term will be 0. Okay, so dV equals to 0. Therefore, dV dt will also be equals to 0. So this whole second term will be 0. Then we will be left with only this term. Okay, so dq dt at constant V. Now we will write it as dq dt at constant V because we have taken the volume constant, equals to del U del T at constant V. Okay. Now what is dq dt at constant V? So it is the heat absorbed by the, so you can write state this as, if you dq amount of heat is absorbed by some system and which results in increase in temperature dt, then you can say dt is the increase in temperature due to an absorption of heat of amount dq. Then unit increase in temperature will be due to the absorption of heat, which is equals to this quantity dq dt. Now this absorption of heat and this increase in temperature is occurring at constant volume. So it will give us the specific heat capacity at constant volume. Okay, so dq dt constant V is the specific heat capacity at constant volume. Now this whole calculation is done for 1 mole gas. Okay, so Cv is basically the molar heat capacity at constant volume. Okay, so next, so this was the expression for Cv. So Cv, the molar specific heat capacity as constant volume is, it is dq dt constant V, which is again equals to del u del t constant V. That is the where you use the internal energy. So it is the change in internal energy with respect to temperature at constant volume. Okay, so so that was for an isochoric process, right? Because we took the volume to be constant. Now if we have an isobaric process, that is P, the pressure is constant, then what will be the equation? Okay, so this equation 3. Okay, so this equation 3, this equation. Okay, so for isobaric process, what will be the equation 3? So on the left hand side we will have dq dt. Now it will be at constant P, and on the right hand side, now none of this term will be 0. Okay, so now this pressure is constant. We have del u del V constant T into del V del T constant. Now it will be at constant P. Okay, at constant pressure. Okay, so what is dq dt at constant P? Okay, so if we follow the previous logic, we can say that it is the specific capacity at constant pressure. So it is the specific capacity at constant pressure. Now this is again for 1 mole of gas. So this is the molar specific heat capacity at constant pressure. Okay, so we have Cp equals to del u del T constant V plus P plus del u del V constant T, then del V del T at constant P. Now we know del u del T constant V is Cv. See, del u del T at constant V is Cv. Okay, so now we can replace del u del T at constant V as Cv. Then we have plus P plus the same terms del u del V at constant T into del V del T at constant P. Okay, so Cp minus Cv is equal to P plus del u del V constant T into del V del T at constant P. So this is the difference in the so this is the difference between the specific heat capacities. Okay, so this is the difference between the you can use the molar because this is per 1 mole gas, molar specific heat capacities. Okay, now for ideal gas we know PV equals to RT. Okay, for 1 mole gas PV equals to RT. Okay, so again for 1 mole gas del U del V is equals to at constant T equals to 0 because for ideal gas. Okay, for ideal gas del U del V constant T equals to 0. Why? Because for ideal gas U is function of only temperature. Okay, for ideal gas the internal energy is taken to be function of only temperature. Now as there is del U del V at constant T, so at constant temperature there will be no change in internal energy. Okay, so this del U or del U term will be 0. Okay, so we have del U del V constant T equals to 0 for ideal gas. Okay, so this term, so for ideal gas what will be value of Cp minus Cv? So del U del V is 0, so we have P plus 0, then this term del V del P del V del T constant P. So for the ideal gas we have this del U del V term 0 and then we'll have P plus 0 into this term del V del T constant P. So for ideal gas what is this del V del T constant P? So we have PV equals to RT, so V equals to RT by P. So what is del V del T constant P? Now as P is constant and R is already constant, R by P is constant and then we'll have del T of T which is 1. So it is basically R by P. So for ideal gas del V del T constant P is R by P. So we have P into R by P. So PP cancels out, we have R. So for ideal gas Cp minus Cv equals to R for 1 mole gas if the gas is ideal. And for the n mole gas we'll have Cp minus Cv equals to Nr.